Okay, we're going to continue section 2.1 that I believe we took notes on during class on Thursday. And this example is in your book. To find the slope of the graph of f of x equal to x minus 3 when c equals 2, we're going to use the definition of the slope of the tangent line. And I've written that definition here for us. The m equals the limit of delta x approaches 0. So the first step is we're just going to plug in c equals 2. So it's equal to the limit as delta x approaches 0 of f of 2 plus delta x minus f of 2 all over delta x. And now, limit as delta x approaches 0. And now for this first part of the definition, we're going to go to the f function right here, right in place of x, and we're going to put 2 plus delta x. So it's 2 from the f function, parenthesis, 2 plus delta x minus 3. All that is 2 times something minus 3, and we got 2 times something minus 3. Now we're ready for the minus sign. And since f of 2 is going to be a quantity, I'm going to use parentheses. And now we're ready to figure out what f of 2 is. So we go back to the f function, and we put that right there for x. So it's 2 times 2 minus 3, all divided by delta x. So just to reiterate, all of this is what I get when I put 2 plus delta x into the f function. And all of this is when I put 2 into the f function, and we are subtracting them. And since we're subtracting, I have to be very careful with f of 2 and put it in parentheses. So I'll continue up here. So that's equal to the limit, delta x approaches 0. Do some distributing, and we're going to get 4 plus 2 delta x minus 3. Now distribute that negative, and we're going to get negative 4 plus 3 all over delta x equals the limit as delta x approaches 0 of, let's see, the 4's look like they cancel, and the 3's look like they cancel. We're left with nothing but 2 delta x over delta x. And those delta x's cancel. So it's the limit as delta x approaches 0 of 2. And the limit of a constant is that constant. Now don't be mad, but we already knew the slope of this graph at any c value, which is just an x, at any x value, because it's linear. F of x equals 2x minus 3. We know y equals mx plus b. We know the slope is 2 constantly because lines, the slope of a line is the same no matter which 2 points you use. So that's a nice little check that's built in for us. We knew the slope should be 2, and by the limit process, we found it to be 2. Okay, this example is saying find the slopes of the tangent lines to the graph of f of x equals x squared plus 1 at the points 0, 1, and negative 1, 2. So they're actually wanting us to do this twice. Consider having one tangent line at that point and another one at this point. I'm only going to go through the 0, 1 point with you, but the second one I think is answered in the book for example 2. So we want to find the slope of the tangent line. We're going to use that limit definition of slope of tangent line. And if I'm going to use this first point, 0, 1, then the c value is the x value. So I will be doing it at c equal to 0. So let's go ahead and substitute that in. And keep on going. So we need to go to the f function. Whoops. And we need to put 0 plus delta x. in right there for the x. So we'll get 0 plus delta x squared plus 1. That's the f of 0 plus delta x. Now we've got this negative right here. So we'll do minus, and I'll immediately do a parenthesis. Now we just go to the f function and we put 0 in. So we're going to put a 0 right there. All over delta x. So if we clean this up a little bit, 0 is such a nice value to work with. 0 plus delta x is just delta x. Plus 1. 0 squared plus 1 is just 1. And I've got a minus in front. So that is the limit as delta x approaches 0 of delta x squared over delta x, because our 1's cancel. And so that's equal to the limit as delta x approaches 0. One of those delta x cancels from the top and the bottom, leaving me with a delta x in the numerator. And I have no problem having a 0 in the numerator. So when I let delta x go to 0, I get 0. So this problem is interesting because this is not a line, it's a parabola. And the slopes of parabolas change, like it's negative, it's 0, and now it's positive. So depending on where these points are on the graph, my slope will be different. And this just happens to be right there at the vertex. That's why we have a slope of 0. We have a horizontal tangent line. And when you do the negative 1, 2, you'll get a different answer. Okay, I have just decided to copy this right out of the book because I liked this first paragraph right here. You have now arrived. You have arrived. You're at a crucial point in the study of calculus. The limit used to define the slope of a tangent line is also used to define one of the two fundamental operations of calculus, differentiation. So that same definition that we used right here on this page, this limit that helped us define the slope of the tangent line, is also the same limit that we can use to find the derivative of a function. And we don't really know what a derivative is yet, but with step by step, right? So this process of finding a derivative is called differentiation. So we have the definition of the derivative. You should pause and write this down. The derivative of f at x is f prime of x equals the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x, provided the limit exists. The only difference is the slope of the tangent line. They used c because we were talking about a specific value of x on the graph, and now this is going to be true for all of the x's in our function. So we switched the notation a little bit to f of x. And right here, I thought this was important. The derivative of a function is also a function of x. This new function gives you the slope of the tangent line to the graph. So the derivative is equal to the slope of the tangent line. They are one and the same. So that's all the derivative is. You hear that word a lot. It's just the slope of a tangent line, provided the graph has a tangent line at this point. The derivative can also be used to determine instantaneous rate of change. Sometimes they may just quickly say rate of change of one variable with respect to another. You might remember from Algebra 1, you learned that slope was called the rate of change. How fast were the x and the y changing? This process of finding the derivative of a function is called differentiation. This is just all terminology. A function is differentiable at x when its derivative exists. and it's differentiable on an open interval AB when it's differentiable at every point in the interval. And then we get into common ways to symbolize derivatives. One is with the prime, f prime of x, and we would just say the first derivative of x. This one is dy dx, and it's red, the derivative of y with respect to x, or simply dy dx. Another symbol is just y prime. This one we don't see as often, but it's derivative with respect to x of f of x. And this one is the derivative of y with respect to x. Derivative of y with respect to x. So just some symbols. I'll try to mix them up and use different ones as we go. Okay, sample 3, we're going to find the derivative of f of x equals x cubed plus 2x by using the definition of the derivative. So the definition of the derivative of x is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. So it's the exact same process that we did in the other example. This is the last example. I believe I'll do like this, and that way I can cover some more of those with you all tomorrow in class. So we're going to say it's equal to the limit as delta x approaches 0. We're going to plug all of this in for the x's in the f function. So it'll be x plus delta x cubed plus 2 times x plus delta x minus, now we're going to plug all this into, well, really, all we're going to do is rewrite the f function. So parenthesis, rewrite f of x all over delta x equals the limit as delta x approaches 0. Now, when we expand this binomial, I'm going to use Pascal's triangle. If you remember that from pre-cal, the first term starts at x to the third and decreases. And the second term starts at 0 and grows. Should have given myself more room. I'll do this again tomorrow if you all want me to. You have to ask. And then we put addition symbols in between all those. Oops. And now we're going to do this part. So just distribute the 2. And now let's do this part and distribute that negative. And then, let's see, I guess we should clean that up a little bit. So this is just x cubed. This is 3x squared delta x. This is 3x delta x squared plus this is just delta x cubed, and then rewrite the rest. Now, lots of stuff should cancel or subtract out. X cubes do, the 2x's do, I think that's everything. So you have 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2 delta x. And amazingly, none of those are like terms, even though they're all super similar. None of the variable terms are exactly the same. So now what I will do is I'm going to erase this little stuff up here. Now what I'll do is try to factor out the delta x in the numerator so those delta x's can divide out. Or I'm just going to take a delta x from every term. So I'm going to take that delta x off. I'm going to take one of those, leaving 2, take that one off and that one off. If you don't like that, what we're going to do is we're going to, switch to blue. I'll factor out a delta x in the numerator just in case you don't like the dividing out thing. Did I do that right? And now I can divide out the delta x's. And I get the limit as delta x approaches 0 of 3x squared plus 3x delta x plus a delta x squared plus 2. And I would be okay if you skipped that line and you just wanted to write what happened when you took your limit. So as delta x goes to 0, this goes to 0. So this whole term goes to 0, and this term goes to 0. And I'm left with 3x squared plus 2. That's our derivative. It seems like a long process, but as you get more comfortable doing f of x plus delta x minus f of x over delta x, the steps become more automatic.